Hi folks, welcome back to Physics with Captain Rod. I'm making this video as a part 2 of a series on how to calculate torque. So what we're looking at is this beam looking geometry which is sitting here vertically. I've got several force vectors acting on it, this 100 Newton force to the right, this 80 Newton force at an angle of 30 degrees clockwise from the horizontal, a 40 Newton force 36 degrees counterclockwise from the horizontal, a 50 Newton force to the left. Distances here. We're going to assume this is a 1 meter distance and a 0.8 meter distance in this example. All right, what we are going to do now is we are going to calculate the net torque about this point that I labeled point A. Now, this is not a Newton's second law problem. I'm not applying F equals ma or its rotational equivalent, which is torque equals moment of inertia times angular acceleration. The purpose of this is just how do you calculate the torque from a bunch of force vectors. So let's go ahead and do that. And I'm going to start with this guy, this 100 Newton force about point A. Now this force's line of action is like this. The force vector's line of action already makes a right angle to this 1.8 meter distance. So we're going to have 100 newtons times 1.8 meters, and that's it. Now we got to decide on a plus or minus sign. Again, torque is a vector quantity. As a general rule of thumb, I usually do counterclockwise positive. That's fairly standard in mathematics. You know, if you think about like if you've had a course in trigonometry, plus 30 degrees was counterclockwise from the x-axis here in quadrant 1. Minus 30 would be the other way. So this force makes this beam want to rotate clockwise, and I'm calling counterclockwise positive. So that torque term would be negative. Next force in line, let's talk about this 80 Newton force. Now, in this example, the line of action for the 80 Newton force looks like this. There are a couple ways to handle that. Method number 1, we could find the distance from A to the line of action where it does make a right angle. Then we can take the 80 newtons times this distance. Or we can take this 80 newtons and break it into components. It has a component this way equal to 80 newtons times the cosine of 30 degrees, and it has a vertical component, which in the picture I'm going to go ahead and put here. The vertical component would be 80 newtons times the sine of 30 degrees. Now it's important to realize that even though I drew this component here, because the 80 newtons has to be the vector sum of these two, this is actually applied basically here at the same point where the 80 newtons is applied. That's going to be important here in just a minute, and I'll explain why. Right? So when we calculate the torque, this component, the 80 cosine 30, is perpendicular to the 1 meter. And that thing is producing counterclockwise torque. So I'm going to put plus 80 newtons times the cosine of 30 degrees. It's my little shorthand for cosine 30 times 1 meter. Okay. Now let's talk about this component. So this component is vertical. An important thing to realize is if you think about like the line of action for the vector component, this component is applied over here. So its line of action basically goes through A. Now, if this force were applied like right on the left-hand side of the beam, technically there's a tiny, tiny, tiny little distance maybe to A, but it's very, very, very small. I'm just going to throw that term away. So we're going to take the component of this force that clearly makes a right angle to the 1 meter distance, and then times the 1 meter. So this force vector has been considered, and we're done. Next, the 50 newtons here. The 50 newtons goes right through point A, so there's no distance. There's no perpendicular distance to point A, so there's no torque produced by this force about point A. If we wanted to, we could put a 0 there. I guess I will for this force vector. The 40 newtons at a 36 degree angle, same thing. The angle doesn't change this fact. The line of action of this force goes right through A. It doesn't matter the direction. I can have a force vector in any direction. As long as its line of action goes through A, there is no torque produced by that force. So I'll go ahead and put another 0. All right, so now I'm going to go ahead and calculate a value. Give me a moment. And I get, if I did this right, minus 110.7. I'm just going to round that to minus 111 Newton meter. The minus sign is indicating that the net torque is in the direction opposite of what I have as positive. So we could say that the torque is 111 Newton meters clockwise. So the purpose of this video is to help show how to calculate torque when a force does not make a right angle to our displacement. And again, big thing is you can either take the force vector, break it into components, one component that is perpendicular, one that's not. Take the perpendicular component times the appropriate distance when you're dealing with force vectors like this. I think I'll just save the other method for another video where you look at the force vector's line of action and calculate the perpendicular distance. I'm going to save that for video 3. So I hope that this video helps with how to calculate torque. Have a great day.